Compared to the capacitor charge and discharge process, the inductor storage and release process might seem a little bit more difficult to visualize. Charges accumulate during the capacitor charge process, and then charges are shed during the capacitor discharge process. Charged capacitors can be isolated from a system because they hold static, non-moving particles. This is pretty easy to imagine. Inductors, not so much. Inductors store and release energy from a magnetic field anytime there is a change in current and must carry current for that magnetic field to exist. The inductor storage and release process is necessarily a dynamic process. The only suitable analogy I've ever been able to come up with to describe the inductor storage and release process is that of a flywheel. Consider a motor shaft with no inertial load and a friction brake that can hold the shaft in position. The moment the motor is energized, the brakes disengage and the shaft quasi-instantaneously snaps to the rated speed. The moment the motor is de-energized, the brakes engage and the shaft quasi-instantaneously stops. If, however, a heavy flywheel is attached to the shaft, there is an amount of static inertia the motor must initially overcome. The moment the motor is energized, the shaft undergoes a brief period of acceleration, and after a period of time, it reaches the rated speed. The moment the motor is de-energized, the shaft doesn't instantaneously come to a stop, but rather the dynamic inertial load continues to rotate the shaft for a period of time before coming to a rest. I like to think of the flywheel effect as similar to the magnetic sluggishness of current in an inductive circuit. It takes time for current to ramp up to the next highest level, and once at this next highest level, it takes time for current to ramp down to a lower level or reverse direction. I like to think of inductors as introducing a type of inertia to a system that kind of acts like a flywheel. If you want to think of inductors in this manner, be my guest. If this analogy only confuses you more, by all means, come up with a better one that works for you, because that's all I've got. Like I said, the inductor storage and release process isn't nearly as easy to visualize as the capacitor charge and discharge process, primarily because it must necessarily be a dynamic or changing process. For those of you with a calculus background, you'll realize I'm going to an almost comical length to avoid talking about derivatives, principally because I don't want to scare those without a calculus background. If you want to use derivatives or rates of change to discuss this phenomenon, be my guest. We'll examine the details of the inductor storage and release process in later lectures. The remainder of this lecture will examine inductors in general and discuss those properties that influence inductance. An inductor's current controlling ability is measured using an inductance figure in units of henries, where 1 henry is 1 volt generated per change in current of 1 amp per second. A 1 henry inductor would be a heavy, fist-sized inductor, especially if it's made with thick wire intended to carry a substantial amount of current. On a more regular basis, you might find commercially available inductors inside the micro or millihenry range. Several properties influence inductance, notably the number of turns in the inductor coil, the cross-sectional area of the coil, the length of the coil, and whether or not the coil is filled with a magnetically permeable substance. The inductor construction formula illustrates this relationship as follows. An inductor's inductance value, L in units of henries H, is the number of turns N squared times the cross-sectional area of the coil in units of meters squared, times the relative permeability of the coil, mu r, a dimensionless constant, times the permeability of free space, mu 0, in units of Webers per amp meter, divided by the length in units of meters. You know that the number of turns in a coil strongly influences an inductor's inductance value because of the squared term. A word on permeability. Permeability is the measure of the core's ability to concentrate the magnetic field. Free space has a permeability of 4 pi times 10 to the negative 7th Webers per amp meter. Magnetic substances like iron have a permeability up to 2,000 times stronger than that of free space. Substituting in the given values, iron therefore has a permeability of 2.5 times 10 to the negative 3rd Webers per amp meter. Consider an air core inductor, i.e. one lacking a core, with the following dimensions: a diameter of 6 millimeters, a length of 25 millimeters, and the coil consists of 100 turns. A diameter of 6 millimeters means this coil has a cross-sectional area of 28.3 times 10 to the negative 6 meters squared. Substituting in our given values into the inductor construction formula demonstrates this air core inductor will have an inductance value of approximately 14.2 microhenries. This is a pretty weak inductance value. If, however, we fill the core with a magnetically permeable substance like iron with a relative permeability of 2,000 times that stronger than free space, application of the inductor construction formula demonstrates an inductor of the same dimensions now has an inductance value of 28.4 millihenries, or 2,000 times that of a similarly sized air core inductor. It makes sense. As a practical demonstration of magnetic permeability, consider the world's worst inductor. I made the world's worst inductor in between classes by wrapping some magnet wire around a pencil, every turn signifying an occasion in which your lazy lab partner showed up late or unprepared. An LCR meter set to measure inductance in the units of henries shows the world's worst inductor has an inductance of 5.5 microhenries, an extremely low inductance value. If, however, I insert a magnetically permeable substance into the core of this same inductor, like a screwdriver shaft, the inductance jumps to 22.7 microhenries. Still a really low inductance value, however much more than previously. Let's take a look at some commercially available inductors of substantially better quality. Here's an inductor large enough to have its inductance value written right on the side, in this case 120 millihenries. The LCR meter set to measure inductance demonstrates it has a value of 118.3 millihenries, super close to the nominal value. As with capacitors, it's a bit of a goat show when it comes to interpreting a particular inductor manufacturer's means of labeling their products, simply because there is no agreed upon standard. Case in point, this particular inductor has no label at all. The LCR meter is showing us that it has an inductance value of 119.9 millihenries. Most likely, this is also a 120 millihenry inductor. Here's another inductor with a code 473J written on the top. This manufacturer is most likely using a code where 47 is the two-digit inductance value and 3 indicates the number of zeros following this number, where the units are assumed to be microhenries. 47 with 3 zeros is 47,000 microhenries, which would be best expressed as 47 millihenries. The LCR meter says 46.4 millihenries, super close to the anticipated nominal value of 47 millihenries. Here's an inductor with a code 106C written on the top. It is way too small to be a 10 million microhenry or 10 henry inductor, so I'm presuming this manufacturer is using a different code where 10 is the two-digit inductance value and 6 indicates the number of zeros following this number, where the units are now assumed to be picohenries instead of microhenries. 10 with 6 zeros is 10 million picohenries, which would be best expressed as 10 millihenries. The LCR meter says 10.1 millihenries, super close to the anticipated nominal value of 10 millihenries. Here's the second worst inductor in the world that looks like it was made by a drunk 3-year-old out of a coiled up coat hanger and a blob of rubber cement. There is no inductance label, however the LCR meter says it has an inductance value of 2.4 millihenries. Most likely this inductor is intended to have a nominal value of 2.5 millihenries. Lest you think all inductors are cylindrical in shape, feast your eyes on these odd forms. Inductors also come in toroidal or donut shapes, don't eat them, and cube-like forms that resemble transformers, an electrical device we'll examine in greater detail in later lectures. All these forms are variation on a theme, that theme being a coil of wire wrapped around a magnetically permeable substance. While we're on the subject of wire, I should remind you that wires have resistance. The longer the wire and the smaller the diameter, the more resistance. Inductors, being composed of many loops of wire, therefore have an internal resistance that often needs to be accounted for. This is to suggest that one can never build a purely inductive element because inductors always include an innate internal resistance. Consider the internal resistance of our previously measured 10 millihenry inductor. This particular 10 millihenry inductor has an internal resistance of 20.3 ohms. Accounting for these values of internal resistance is often done by including the internal resistance in series with the inductive portion. It's important to realize the internal resistance is an innate, inseparable quality of the inductor. The 10 millihenry inductor with an internal resistance of 20.3 ohms could be modeled as a 20.3 ohm resistor in series with a 10 millihenry inductor, where only the external terminals are accessible, implying that you cannot get one property without the other. I should note that the internal resistance of an inductor is not necessarily a constant, unchanging quality. We'll examine how frequency affects inductive impedance in later lectures. Moving on. Let's briefly examine inductors in series and parallel before we bring this lecture to a close. If you recall, capacitors in series and parallel presented some unexpected twists and turns and necessitated all sorts of nonsensical stupidity to compute total capacitance and voltage and current for individual capacitors inside these relationships. Not so for inductors. For all intents and purposes, series and parallel combinations of inductors can be treated just like resistors when it comes to calculating total inductance and voltage and current for individual inductors inside these relationships. Inductors in series add up. Given a series combination of 2 or more inductors, the total inductance of the series relationship is L1 plus L2 plus L3 and so on. The total inductance of this series relationship is 120 plus 47, or 167 millihenries. 2. Easy. If we know voltage across this series combination of inductors to be 12 volts and current through it to be 20 milliamperes, we can use series circuit properties to determine how voltage is apportioned and how current flows through individual series elements. Again, just think of the inductors as if they were resistors. Current through elements in series is the same. Current through L1 is 20 milliamperes, as is current through L2. Voltage across inductors in series is directly proportional to inductance value. I like to use a variation of the voltage divider rule, where voltage across the inductor of interest, Vx, is equal to the inductor of interest, Lx, divided by the total inductance for that series path. In this case, L1 plus L2, times the total voltage across that series path, in this case 12 volts. Substituting our given values for L1 indicates that inductor 1 experiences an 8.6 volt drop. Application of Kirchhoff's voltage law demonstrates that inductor 2 experiences the remaining 3.4 volt drop. Let's now examine parallel inductors. The total inductance of a parallel combination of two inductors is the product of the two inductance values divided by the sum of the two inductance values. L total equals L1 times L2 divided by L1 plus L2. When presented with a parallel combination of two or more inductors, 1 over the total inductance value is 1 over L1 plus 1 over L2 plus 1 over L3 and so on. If we know voltage across the parallel combination of inductors to be 12 volts and total current into it to be 20 milliamperes, we can use parallel circuit properties to determine how voltage is apportioned and how current flows through individual parallel elements. Again, just think of the inductors as if they were resistors. Voltage across elements in parallel is the same. Voltage across L1 is 12 volts, as is the voltage across L2. Current through inductors in parallel is inversely proportional to inductance value. I like to use a variation of the current divider rule, where current through an inductor of interest, I1, is equal to the inductor not of interest, L0, divided by the total inductance for that series path, in this case L1 plus L2, times the total current into the parallel relationship, in this case 20 milliamperes. Substituting in our given values where inductor 1 is our inductor of interest and inductor 2 is our inductor not of interest, demonstrates inductor 1 experiences 5.6 milliamperes of current. An application of Kirchhoff's current law demonstrates inductor 2 experiences the remaining 14.4 milliamperes of current. Alright, that's about it for now. I'm certain all the juggalos out there still have questions about inductors and magnetism. However, I'm hoping those of you that aren't dirty paint-huffing subhumans now have a greater appreciation and understanding of inductors and electromagnetic interaction. In conclusion, we introduced the inductor, an electrical device that can store energy inside a magnetic field inside a coil of wire. We examined basic electromagnetic interaction, the concept of inductance, inspected inductor construction, discussed how properties like cross-sectional area, number of turns, coil length, and magnetic permeability of the core influence inductance. Additionally, we briefly discussed the shoddy and unpredictable means manufacturers use to label inductors and how to measure inductance using an LCR meter. Finally, we learned to calculate total impedance of series and parallel relationships of inductors. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.